Okay, everyone, let's get started. Sorry, I running a little late today. So last lecture I was talking about Lab 4, but there's a lot of details in Lab 4. It's pretty complex. It's a big jump in difficulty from the last lab. And the reason is because we're going to write, this is the only lab where we're going to write a low-level device driver for the SP32. So as I mentioned, the objective is to basically have it play audio through the PWM. So we're going to load an audio file with we have a Python script that allows you to open an MP3 or WAV file and then just convert it into a C constant array. So the audio file will just become an array of samples. And then the script also tells you what the sample rate in the file is. And so your code on the SP32 is going to have to adapt to whatever rate the audio was intended to be played at. Does that make sense? Okay, so you're going to play the audio, which can be music or something like that, and then at the same time we want to use the LEDs on the board to visualize the audio somehow. So that requires that you interface with both of those peripherals using low-level code, and then you also need to have a way to have your code keep the audio going while at the same time update the LEDs. So there's kind of you're going to have to have some kind of loop in your main function that alternates between those two things because we only have one processor core. You guys with me? Okay, so you're going to have to time multiplex the processor. Okay, so I updated the lab sheet and posted it this morning. And I put the slides that I covered on Tuesday on there as well. I still need to post the Python script. I'll put that on Blackboard today. So I just wanted to go over this one more time just to make sure everyone's clear on this. We'll have it due in 2 weeks, and then we have one more lab after that where we'll be controlling a motor. And in that last lab is going to be using the built-in drivers, and we're also going to use free RTOS, the little thin operating system that they have on there. So the last lab will be more abstract, whereas this lab is more low level. Does it make sense? So we have 2 more labs, and then there's also 2 more lectures that I have to give. I'm going to give a lecture on control theory, and I'll start that today. And then there's a last lecture on real-time systems, and then that'll give us some material to cover in the final exam. So 2 more projects, 2 more lectures in the final, and that's all we have for the rest of the semester, okay? So in this lab, we have 2 peripherals that we're dealing with. One's called RMT, that was originally designed for an IR remote, but we're using it for the LEDs. And then there's one called LEDC, which we're using for the audio, okay? Which is confusing because the LED peripheral is not being used for the LEDs on the board. Okay, so the naming is weird there. The LEDs are an example of another protocol that we didn't cover when we talked about protocols, but it's kind of a proprietary protocol that relates specifically to the WS2812 LEDs. These are the LEDs that make up like the big, like the electronic billboards, Jumbotron type things, and the really nice Christmas lights displays. The idea is it used to be in the old days that if you wanted to control multiple LEDs, you needed like basically a pin for each LED, right? In fact, when we originally designed this course, we dealt with that problem using a technique called Charlie plexing, which is a way that you could reduce the number of pins required for the LEDs. But either way, it wasn't really practical to control a large amount of LEDs in an embedded system until these guys came out. And the innovation here is that you have all the LEDs connected on a serial chain, just like kind of like JTAG or daisy chain SPI, and they're asynchronous. You don't have to worry about sending a clock. And the reason is that they have each one of the LEDs themselves has their own clock, their own kind of, I don't know, like a wall clock, timekeeping device, like their own crystal. which sounds kind of crazy, but so that allows them to be asynchronous like UART. So remember with UART, you had two ends of the channel and they both had their own clock and they just agreed upon a bit rate. In this case, these LEDs have their own clock, but they can detect how long the signal is high versus how long it's low. So that's just how you encode the ones and zeros here. So a 0 is you hold it high for 400 nanoseconds and low for 850. And if you want to send a 1, you hold it high for 850 and low for 400 or whatever the case may be. I have the table on the next one, next slide or next somewhere here. Actually, the table was on the slide. It's written in here. But the idea is that you have a high time and a low time. And so, and the time is in terms of nanoseconds. So presumably on these LEDs, they have a way to measure nanoseconds. And then in the case of our software on the ESP32, we're using the RMT, right? And the RMT allows you to basically specify high and low time in terms of 80 megahertz cycles, right? 80 megahertz is like 1.25 nanoseconds per cycle or something like that, right? So you're just counting cycles essentially, right? Okay, so that's the LEDs. And of course, if you want to, you set each color of LED in order according to where they appear on the strip on the chain. And so, and then when you want to reset their values, you hold the data in low for 50 microseconds. Okay, is that clear? I went over that really fast because I'm just reviewing that from last time. Okay, so then we have this remote control transmitter. So the idea is that we can't really bit bang this. We can't just control this pin directly from software. We want to have some hardware component control this pin for us, right? And that way the software doesn't have to be constantly involved in this, right? Now, it still has to be pretty involved though, because the way the RMT works is that you program it with a series of these pulses, which allow you to set the color of one LED. And then when it gets done transmitting that, you have to go and reprogram it again. So basically, the software has to become involved after setting the color of each LED, right? Which is, still fairly frequent, but at least you don't have to have bit level granularity, here, right? So the RMT is taking some of the burden off the software. Okay, so right, so here's where things get a little tricky. So there's a few things you have to do to set this stuff up, and I tried to put as much detail in this lab sheet as I could because there's a lot of details, but they all involve just setting registers. So we talked at the beginning of the course about bit twiddling and setting control registers and reading status registers, but we never really got to do it until now. So this is supposed to apply the knowledge that I covered in the first, basically the first lecture. So we have a couple registers here that are used to basically just turn off and turn on certain peripherals. Each bit maps to a peripheral. There's 32 bits, and it looks like 27, 26, and 25. There's 3 of them that aren't used, so it looks like there's 29 peripherals that you can turn on and off with this register. It's called the System Periph Clock Enable Register. And you can see there's a whole bunch of them here, including CAN, Controller Area Network. That's the protocol used to talk to your car and move the steering wheel. SPI, there's several SPI, squared C channels. Bless you. There's also a PWM, which is kind of interesting. I just noticed that now, which seems like that would be doing the same thing as the LEDC. But we also have the LEDC and the RMT, so you want to turn both of those on. The reason why you have to turn them on is because not all the peripherals are turned on by default in order to save power. And then there's a reset as well. You can use this other register, System Periph Reset Enable. You can use that to pulse a reset bit for these individual peripherals. So in other words, if you write a 1 in here and then write a 0 in this register, that's actually pulsing the reset bit for that peripheral. You guys with me? You guys remember from 611 that most, actually all sequential logic circuits have a reset, right? Okay, but these are they're pretty simple. They're basically just a global register. The complicated part for me is figuring out what the address of these guys are. So I mentioned that there's a read reg and a write reg macro you can use to read and write these addresses. The problem is that when you look in the manual, these addresses are given as relative to the base address for different base addresses. In this case, this register is 20 bytes after the base address for the system registers. So you have to look up the base address and add 20 in order to get the real address, the absolute address for this. But in the lab sheet, I have calculated all those for you. They're in a table at the bottom just because I think it's tricky to find those addresses. Okay, so then in order to set, so for the RMT and the LEDC, both of them have two phases of operation. The first phase is you initialize it, and the second phase is you actually use it, right? So you're going to initialize both these peripherals first, and once they're initialized, then your software just goes through a loop where it updates the LEDC and then updates the RMT and updates the LEDC and updates the RMT. And when I say update, I mean send the new color or send the new sample out to the speaker. Does that make sense? Okay. Okay, so the initialization for the RMT involves just a few different registers. There's this RMT sysconfig, and I tell you exactly what to set in there. The RMT channel 0 config 0 reg, which is shown here, and there's a few things you want to set in there. They're all listed there. And then after you configure the RMT and the LEDC, or actually the order of this doesn't really matter, because you need to connect both these peripherals to pins. And we also, I talked about this briefly too in a while back at the beginning of the semester. So in order to connect these guys, there's this GPIO matrix, and I'm only showing the output version of this. There's an input and an output version of this GPIO matrix. The output is a mux and the input is a demux, right? But we only care about the mux part. So the mux is just taking signals and muxing them to a pin, right? Now you might say, well, wait a minute, there's more than one pin. Each mux only has one output, so how does that work? Because there's multiple muxes. There's one mux for each pin. Every pin has its own mux, and every pin therefore has its own control register to control the mux, right? So basically, if you want to control pin, say 5, you have to figure out what the address of the mux control is for pin 5. You guys with me on that? So each one of these guys has their own address. So basically, you set this select, and not only that, but there's a different code for each one of these peripherals. So the RMT and the LEDC have their own code, meaning what you put on the select, and I give you those in the lab sheet. You don't have to look those up. There's also this IO mux, which kind of blocks it blocks this guy. This guy outputs, and then he potentially gets blocked by this guy. But don't worry about it. It turns out, I didn't even know this until last night, but apparently you don't have to worry about this mux because by default, when you bring the ESP32 up, it's automatically set up to forward the GPIO mux. So you don't actually have to even worry about the IO mux. We did last year, but with the new chip, not a big deal. You just have to worry about this guy. Okay, so that's the GPIO mux. And there's the codes that I was mentioning. Okay, so, and then of course the pins are important here too. You have to make sure that you map the right pin. So basically, the LEDC, which goes to the speaker, well, it goes to a filter and an amplifier and then to the speaker, but basically that pin is 14. And so you need to figure out what the mux address for 14 is, and then you set it to 73, which is the code for LEDC. And then pin 33 is the one that goes out to the data out, the serial pin out to those LEDs. That's pin 33, and then that code for that is 81. So basically, find the address for pin 14, write 73, find the address for 33, write 81, right? That's all you got to do. Now there's some stuff here about what the other bits in the GPIO function do, but they're not really relevant because by the default settings are good for those, right? Just give you, this is just background. I probably should get rid of, I thought about deleting this, but I think it's kind of useful. You can, for example, invert a pin, that kind of stuff, but you don't have to worry about that. Okay, and then, right, and then the RMT data is just an array it's like a script. You say, I want you to be 1 for this many cycles, 0 for this many cycles, 1 for this many cycles, 0 for this many cycles. And so you go through all that, and then when you're done, which you're going to be done after 24 of those, because there's 24 bits that are sent to each LED. Because the LEDs just require color. They don't care about anything else, just color. And so there's 8 red, green, and blue, right? So once you send the color out, there's no other control bits, there's no handshaking bits, nothing. You're literally just 24 bits, 24 bits, 24 bits. You're just sending a sequence of 24-bit values across, which will set up each LED in order of their connection, right? So in the case of, we have 100 LEDs. If you want to do the 99th one, it's going to be the 99th 24-bit value will go to that guy, right? Assuming you don't have that reset period, that 50 microsecond downtime, which puts them all in programming mode again, okay? So they're all programmed in order. Make sure you zero terminate that guy though. Okay, so this is the steps for how to transmit on the RMT. And so I'll give you those steps. They're pretty straightforward. Just follow the steps. And then the one thing that is a little weird is once the RMT is in the process of sending 24 bits, it becomes disengaged from the CPU. They're asynchronous, right? The CPU is going to be doing its own thing. RMT is going to be sending the bits. So you need a way for the CPU to know if the RMT is finished sending 24 bits, right? So there's a register called interrupt. This is an interrupt register and an interrupt clear register. Now you might say, wait a second, I thought you said if there's an interrupt, we go into an interrupt service routine, right? Yeah, normally yes, but in this case we're just going to pull. We're going to pull this interrupt register. We're not going to have an ISR. It would be better if we had an ISR though, but we don't know how to. I don't know how to do that. If any of you can figure that out, you're welcome to use an ISR instead of having to keep polling this register to see if the thing is done, right? Okay, does it make sense? Yes?
Would you have to pull anything in regards to figuring out how a matrix would work when programming the LED?
The matrix? The LED? No, the only thing you have to do for the LED is you're just checking. The intent here is to have the software know when each LED is programmed, right? So you can, now you might say, why does it have to know that? Why isn't this automatic? Well, the reason it's not automatic, here, let me back up. I think I understand where you're getting. So the reason why it's not automatic is this script that says high time, high time, low time, high time, low time, high time, low time. You only have 384 entries in this thing. That's the problem. If you had more entries in this RAM, you could program all the colors, right, for all 100, right? If you had 2,400 entries in this RAM, then you could do it all in one shot. That would be awesome. Like you could literally just write this array once and then and send everything out, and all the LEDs would get programmed, right? The problem is they don't have 2,400 entries in here. There's only 384. So as a result of that limitation, you have to write one color at a time, wait for it to finish sending that color, and then go back and update this array again and tell it to go again, right? Of course, you can, I was going to say you can update the array while it's sending, but actually I don't think you can do that, because if you update the array while it's transmitting, you'll probably bork it, right? You don't want to touch this array until it's done transmitting, otherwise you'll step on it, right? So, you guys with me? Like you don't want to update the colors, you don't want to update the bits, the high and low times until it's done, right? So that's why you need the interrupt. Yeah.
Would it often be advised to use either a stack array or take, like, say, at least one pointer and then use said pointer to store the value?
You can do it however you want. That's the other thing too. Last year we had 5 LEDs, right? And so we basically just said, use the 5 LEDs as a power meter. Like when the audio gets louder, have more LEDs lit, right? And have them be a hotter color. Now we have 100 LEDs. And we haven't really decided how to adapt this to 100 LEDs. I was thinking originally, I would like to do a spectrum analyzer where you have like a spectrum, like do a Fourier transform, but I'm not going to cover how to do that, right? And plus, I don't even know if the ESP32 has enough horsepower to do that. If any of you want to try it, you're more than welcome to. So I'm going to leave the visualization part up to you guys, right? You could just have it like have a scale of 100 LEDs and just basically show the power over a scale of 100, right? Or you can just change the color of all the LEDs to indicate the volume, the power of the audio, right? I'm going to leave that up to you because you guys, as long as you update the LEDs while you're playing the music, that's all I care about. Does that make sense? Do something, see if you can come up with something that looks interesting, because Alex and I couldn't. We failed miserably to come up with an idea for this, right? You can also just use the 5 LEDs if you want and just do it the way we did it last year. I'm actually fine with that too, because if you can use 5 LEDs, you certainly could use all 100 if you wanted to, right? So I really don't care even if you don't use all the LEDs, as long as you use them for some purpose, right? You guys with me? Okay, yeah. So the lab sheet is just written right now for the 5 LEDs, right? That's at the bottom. Okay, so then we have the steps for transmitting, and then we talk about the LEDC, how to initialize that, and how to use it. So the LEDC is, I don't really like this. I think this is kind of bad, but we haven't come up with a better way to do it, frankly. So the RMT, you have to wait for the interrupt to see when it's finished sending 24 bits, right? And sending 24 bits, even though it's like 1.25 microseconds per bit, and you're sending 24 of them, so whatever 24 times 24 plus a quarter of 24, which is what, 6? So 30. So 30 microseconds. So it takes 30 microseconds to send one color to the LED strip, right? You guys with me? 30 microseconds. 30 microseconds is a pretty long time for a processor that's running at 200 megahertz, right? But the LEDC, on the other hand, you have to send a new audio sample to that every, well, whatever the sample rate is, 8 kilohertz, right? So that's actually slower, I think, maybe. So actually, maybe it works out. But the idea is that with the LEDC, you're sending one sample at a time. So you're having to update the LEDC for every audio sample, which is like, depending on your audio file, it could be, like if it was really good audio file, it would be 48 kilohertz, right? But, as I mentioned in class, probably you're going to have a lower sample rate because of space limitations. You guys with me? Okay, so is there any questions about that? All right, so I'm not going to go through every detail here because there's a lot. Most of this lab sheet is just, you having to, follow the instructions on how to set this stuff up. So this is basically just an exercise in being able to update these registers to write the driver and debugging, because if it doesn't work, you have to go in and figure out, like, if you're off by 1 bit or something. So it's a chance for you to write a driver and to debug it. Okay. Oh, by the way, I don't know if I ever mentioned this in lecture, but when you guys run the Arduino, you're actually getting version 1 that doesn't have debugging capabilities. But if you run Arduino-IDE, just a different command, if you add -IDE, you get version 2, and the debugger should work on there. You guys with me? When I say debugger, I mean setting breakpoints and inspecting variables and that kind of stuff. Although a lot of you just use your own laptops, right, for these things too, Platform IO. But if you use the lab machines, I recommend you start using Arduino-IDE. It just so happens we have version 1 and 2 installed on the lab machine, differentiated by the command. Okay, any questions? Okay, so I still have to post the Python scripts for reading the audio, but I think everything else is up online. Okay, so let's talk about the next topic here for the class. So the next lecture is a very light introduction to digital control theory. Are any of you taking control theory? That's electrical 331?
I already took it.
Okay.
It was rough.
Okay.
We got through a little bit of Z transform, but it was mostly just analyzing Laplace plots, I believe, and Bode plots.
Okay. Okay.
We didn't get to. I skimmed through it. We didn't get to some of the other transformations like Z transforms, which I believe is covered in digital signal processing.
Yeah, I'm going to talk a little bit about Z transforms. So there's, that's a good point. So just to clarify, the control theory that you learned was basically like a continuous control theory, like a math class, basically. It was not applied.
It was more analog, and from what I know, I think some of the more wilder stuff you get into is 531, but even then you have to specialize, you have to declare a minor in electrical engineering and then take that into 500 class.
Well, it's not even analog. It's worse than that. It's not even a question of it being analog. It's continuous in the sense that if you have an S domain, control theory, controller, right? You literally cannot implement that in software. It's impossible, right? There's no way to do it. You have to discretize it. So you can either discretize it through the Z transform or through a state space type transform. Yes?
Yeah, I'm in 531. We're doing all this.
Oh, you are? Okay, good. All right, well, you can tell me if I make any mistakes here then, because this is a very, very brief introduction. The reason we're covering it here is because this class, the theme of this class is cyber physical systems, which is involves control theory, right? You want to control something. You want to control. The intent of this class originally was to build some kind of robot. We just haven't gotten to that point yet. So I just want to cover a very light introduction just so you can say you know it. If you were at Clemson and you were a computer engineer at Clemson, control theory is a required class there. And it's very common for this to be required as part of a computer engineering curriculum. It's just not here. So this lecture is intended to kind of fill that gap. But I'm not going to go into, obviously it's one lecture. They teach whole classes on this. They teach a class on this in obviously electrical, but also in mechanical engineering as well. So obviously this is a very small introduction, right? Okay, so for those of you, so I mentioned, cyber physical systems involve controllers of some kind. A cyber physical system is an embedded system, which is a special purpose computer that links sensing, computation, and control to the physical world. So this is where you have a computer exerting its control in the physical world, like in a robot or a self-driving car or a drone or something like that. So the idea is that you have a controller that's controlling a plant. The plant is the physical object. And so by control, what I really mean is regulate. And by regulate, what I really mean is that the controller is trying to put the plant into a desired state and keep it there. And by state, I mean like, you're trying to keep the car centered on the road, or you're trying to keep the drone at a specific altitude, or you're trying to keep a cube balanced on one of its points, right? Something like that, right? Why do they call it plant? Well, because this was originally, the terminology is antiquated. It was designed for industrial automation originally, but nowadays it's used for robots and micro drones, that kind of stuff. So focusing system in a camera, that kind of stuff, autofocus. So, but they still call it a plant, which is crazy that they still use this terminology. So basically you have a controller and generally you have some kind of a set point that comes from the user. So this would be like an altitude for the drone. And then the controller is trying to keep the plant at that set point. And it does that through some sort of output to the plant. This is like an actuator, control for an actuator. And then the plant optionally has measurements that are read back by the controller. This is if you have a closed loop controller. An open loop controller doesn't have this feedback connection. Okay. So an example. Oh, and then the plant. And this is the part that's kind of dicey. The plant has another input called disturbances. And a disturbance are things that basically make life difficult for the controller. Disturbances are supposed to be totally unpredictable, right? And so, for example, like if you have a self-driving car, a disturbance might be bends in the road, right? So you're trying to drive straight and the road bends, that makes it difficult. And if you're a drone, a disturbance would be a gust of wind, right? But disturbances are difficult to model. So this is why often designing control systems is kind of a trial and error process because there's no way to really model disturbances accurately. This is why if you're, SpaceX and you're trying to land the rocket, you got to blow a bunch of them up before you can get it right. And there's just no way. There's no way to simulate this and do it entirely virtually, right? Okay, so I mentioned, so the reason why this is important for computer engineers, why is this relevant to you? You might be thinking I'm not electrical. It's because, if you work for Tesla or Nest or a camera company or a drone company, you're going to have to, deal with this or have a little bit of familiarity with it. Control systems, I mentioned, can be open loop or closed loop. A lot of them are open loop, meaning that there's no feedback signal. So the controller just actuates the plant without any way to read what the plant is doing, right? Which is frankly retarded. I don't know why anyone would do it that way, but as it turns out, a lot of devices actually work that way. For example, the two that always piss me off, the toaster and the clothes dryer. So the toaster, yes?
So given let's say a laundry machine, having like some simple $600 machine, if you have, say, just a timer and a setting of heat, that would be your open loop system.
Right.
But if you want your clothes to be dried with a specific amount of dampness, that would be a closed loop. That would be a closed loop.
Exactly. So I bought the most expensive dryer I could find. That's the Samsung AI Family Hub washer dryer combo system, and the clothes are always wet when they come out, always. So there's like no sensor in there. Same thing with toasters. Toasters. This is what really bugs me because sourdough bread toasts much slower than regular bread, as do bagels, as compared to white bread, right? So why in the world would you design a toaster that doesn't incorporate some kind of a sensor to measure how toasted or how hot your bread is when you have certain breads that you put in there that are more resistant to heat than others, right? It drives me crazy. But anyway, these are basically open loop systems. There's no sensor in any toaster, and evidently there's no sensor in any dryer, clothes dryer, even though they may claim that there is. It doesn't evidently work. Okay, but a closed loop system is if you had a toaster with a sensor that would measure how toasted your bread is, and then it would just keep heating the bread until it reached the desired level of brownness, and then it would pop up the bread, right? So that would be the way to go. But I've never found a toaster that works that way. So the idea, the set point would be a level of toastedness, right? And then the optical sensor would measure the color of the bread, and the difference between the color you want and the color it is would become an error signal that would go into the controller and would determine essentially the cook time, right? Or the cook temperature or whatever the case may be. And so there's a few other terminology things here. So the output from the controller to the plant are usually called manipulated variables, and there can be one or more of those. And then the readings from the plant, the measurement from the plant are called process variables, and there can be one or more of those. If your controller has more than one manipulated variable and more than one process variable, then it's a multiple input, multiple output controller. However, in this class, we're only dealing with single input, single output controllers, right? So there's one, in our case, there's just one of each, right? Okay, so now this is where we get into the whole question of continuous versus discrete. So plants are usually physical things, physical phenomena, physical devices, all of which are governed by differential equations, basically. So generally speaking, your model for a plant's behavior or its dynamics means how it changes over time, is going to be modeled as differential equations, specifically ordinary differential equations which have that are dependent on only one independent variable, time, right? So everything is a derivative with respect to time or an integral with respect to time. They're not partial differential equations, they're ordinary differential equations, right? Now, the problem is how do you talk to an ordinary differential equation? You do it with another ordinary differential equation, except both of them are continuous, right? They're not discrete, right? But generally, at least when you first start talking about control theory, you just model the controller and the plant as a ODE, right? That's kind of the naive way to, or the basic version, the basic way to look at it, but not very applied, right? Okay, so now the ordinary differential, by the way, it's not any ordinary differential equations. Typically, at least in an introductory class, you look at one specific type of ordinary differential equation, which is called a linear time-invariant system. Linear time-invariant is it's a linear ordinary differential equation. What does that mean? It means that all of the derivatives and integrals of a variable or signal are linear, meaning that they're just constants, scalar constants, meaning that you cannot multiply two variables against each other, or you can't square a variable, right? You're not allowed to do any of that. They're linear. Now, this is the thing that's some of you may be confused by, because normally when you think of a linear system, you think of a straight line, right? But when you think of an ordinary differential equation, you think of a curved line, right? So how can an ordinary differential equation be linear? Well, it's a special type of linear that refers to specifically the way that you multiply values against variables, right? Functions of time. Okay, so that's what we're talking about when we say linear, right? Now, can you have nonlinear systems? Yes. In fact, in real life, every system is nonlinear. A resistor, for instance, is a linear thing, but it's not really, because the resistance of a resistor depends on temperature, so there's a nonlinearity. Likewise, a spring most people think of a spring as linear, but it's not, because if you push a spring in enough, it stops compressing and it's got that nonlinearity. Likewise, if you pull a spring apart too far, it breaks in half, and that's a nonlinearity. But so all real things are nonlinear, but typically, at least at first, you just assume everything is linear, right? When you do this stuff. Okay, so right. So and then so what it really means, linear is state terms or signals or variables, whatever you want to think of them, are multiplied by constants only. They can't be multiplied by each other. And time invariant just means that the constants themselves are constant. They don't change over time, right? Okay, so an example of that is, so what I'm talking about specifically when I say variable or signal is, for example, x of t. So x of t is a time-varying signal. We could take the first derivative or the second derivative of that with respect to time. Likewise, we could take the first integral, second integral, etc. And those are just variables, right? And then we can multiply those derivatives and integrals by constants. Okay, so an example of that is the force is the mass, which is a constant, times acceleration, which is the second derivative of the position, right? So that would be a linear system. Now, the problem is that it gets very cumbersome to keep everything in the time domain. So normally these are written out, these are worked with in the S domain, the Laplace domain. The Laplace domain is the frequency domain, right? So you guys are familiar, I guess you guys probably covered this in circuits 1 or 2, right? Okay, so the idea with the Laplace domain is that if you have a variable, say x of t, you capitalize the x. Yeah. And then it becomes x of s instead of x of t. And then if it's a derivative, you multiply it by s. And if it's a second derivative, you multiply it by s squared. And if it's an integral, you divide it by s. That's it. It's not real complicated. It's pretty simple. The problem with Laplace is that once you go from time domain to Laplace domain, there's not really any going back. That's the problem with it. But it makes things very easy to work with it, right? So for example, if I have mass times acceleration equals force, that would be written as mass. So m, that doesn't change, it's still m. And then capital X instead of lowercase x, where x is the position. And then you multiply it by s squared to denote that it's the second derivative with respect to time, right? And then f just becomes, f of t just becomes f of s, or simply shorthand is just capital F, right? You'd leave out the of s, right? But that's really f of s, right? Okay, so yeah, that's it. That's pretty simple. You just have to remember that derivatives multiply by s and integrals divide by s, right? That's pretty straightforward. The problem is, where it gets a little bit more complicated, is the fact that an ODE is an equation. It's not, it's just an equation. You don't really have a notion of inputs and outputs. And in order to build a control system, you got to have inputs and outputs. Why? Well, because manipulated variables and process variables, right? They're inputs and outputs. But an ODE doesn't know what the hell an input or output is. It's just an equation, right? It's literally just an equation. It's just two sides that are balanced, right? So in order to come up with this concept of inputs and outputs, there's this notion of a transfer function. Okay? The way a transfer function works is a transfer function is a ratio where you set the ratio up to be, you put the output variable on the top, and this is in the Laplace domain. So if your output variable is, say, force, right? I want to change the force, so that's my output, right? I'm doing something to affect the force. So that's my output. And then the input, whatever the input is, like voltage, right? I want to increase the voltage that makes the thing go faster, imparts more force on it, right? That would be in the denominator, right? So what this boils down to is algebra. You have to just essentially rearrange the equation using basic algebra to get the output variables on the top and the input variables on the bottom. That's it, right? Now, once you have that, you have a transfer function. Now, remember, keep in mind a second here, we're talking about single input, single output systems, right? This is not MIMO, this is CSCE system. So in a CSCE system, there's only two variables, right? So one's an input, one's an output. So you move all your variables to one side of the equation, right? So what's on the other side of the equation? Well, the other side, it turns out, has nothing but s in it. Actually, well, it's a polynomial. It's a ratio of two polynomials of s. Right? Does it make sense? So essentially, the transfer function is, at least in a CSCE system, all the variables are on one side, and the other side is literally just polynomials of s. Okay? Make sense? So, for example, do I have an example? Oh, sorry. Yeah, actually, sorry. This is an example. So if it's mass times acceleration equals force, let's say force is my output and x is my input, then it's F over x equals ms squared. Right? How did I get that? Well, I just took this and I just did some algebra to get that, basically. Right? That's all there is to it. Very simple. Okay, so that's a transfer function. So here's another example of one. So let's say I have u of t equals y of t plus the derivative of y with respect to t plus 6 times the integral of y with respect to t. So the first thing you do is you take the Laplace transform, which is very simple. You just basically capitalize everything and change of t to of s, and then the derivative adds an s multiplier and the integral adds a 1 over s multiplier. Okay? Yeah, that's it. So that's it. And then you're like, well, okay, but that's not a transfer function. How do I make this a transfer function? Well, you have to decide what the inputs and what the outputs are. Do we want it u relative to y or y relative to u? You can go either way. Depends on what's going on. So I think in this case, yeah, so in this case, I'm assuming u is the input and y is the output. So my transfer function has to be y over u, right? Output over input. And so you have to do some algebra here. So how do you do that? Well, you factor out, you start with this equation. You got to create this ratio, right? So you factor out y of s here, right? So if you factor out y of s, you end up with this 1 plus s minus 6s minus 1, right? I just factored out y of s, and then of course, I have to, well, I guess I have to divide both sides by u of s, and then divide both sides by this thing, right? So, yeah, so basically, y over u is 1 over 1 plus s minus 6s to the minus 1, right? So this becomes my transfer function describing the input-output behavior of that ODE, that LTI, right? Okay, so yeah, that's all you got to do. Now, what else do transfer functions do? Well, transfer functions are cool because they're composable. So if you have a transfer function, let me back up here. So transfer functions are meant to represent a plant and also a controller, right? Now I mentioned that technically the controller, if it's a computer, it can't do an S-domain transfer function, right? But let's just assume for the moment that it can. And by the way, there are continuous controllers, they're just not computers. So one of the examples of that is if you have a greenhouse. Greenhouses have to have a constant temperature inside the greenhouse, regardless of the outside temperature, right? So the way they work is, basically, if it's too hot in the greenhouse, you need to open a louver. If it's too cold in the greenhouse, you want to close the louver, right? So the way that works is the louvers work by thermal expansion, right? So if the louvers get hot because it's too hot in the greenhouse, they open automatically through thermal expansion, not through a computer, right? So that is a continuous. That's a transfer function. But it's not a computer. Okay. Anyway, so if we assume that we're conceptualizing the control and the plant as transfer functions, then we need to connect them together somehow, right? So how do you do that? You have this notion of an internal signal. So if U is my set point, Y is my manipulated variable, and then I have an input of Y into the plant, and then G is the output of the plant, which is, you can think of that like the process variable, right? What you end up with is this Y is common between these two guys. So what I want to do is I want to connect these guys together. I want to treat this like a two components that I'm going to plug in. So you can do that. And then once you do that, you want to then conceptualize the combination of the plant and the controller as a new transfer function, right? I want to compose them. So how do you do that? It turns out with transfer functions, it's very simple. You just literally multiply them together, right? So this is Y over U, Y output, U input, so it's Y over U. This is G over Y, because G is the output and Y is the input. If you multiply these guys, Y cancels out, right? Why is it? Well, you want it to cancel out because this Y becomes part of the plant. I mean, it becomes part of the it gets absorbed into the composed transfer function, right? So you just multiply these two guys together, and that gives you a new transfer function that is G output relative to U with the Y gone, because the Y cancels out in the algebra, right? So literally, you can multiply transfer functions together to give you an open loop transfer function, right? Now this doesn't have the feedback yet, but we have open loop because they're just mashed together essentially. But I still have one global input and one global output. There's no feedback yet. Okay. All right. So what is the goal here? What are we trying to do? Well, we want there's two goals. One goal is we want to have the system be regulated, right? So we want to be able to bend the physical world to the will of the controller. We want a controller to be able to put the physical thing into a state and keep it there, right? But there's another goal too. The other goal is stability. Because if you design, so most physical systems are unstable, meaning that you can give them a bounded input and you won't necessarily get a bounded output. You could give it basically a bounded input, and the output can go to infinity. Right? That's an unbounded system. The controller is generally going to be, well, the controller could be bounded or unbounded, but the point is when you put them together, the system that's resulting from that should be bounded. Does that make sense? We don't want it to get into this state where it oscillates and oscillates and the magnitude gets bigger and bigger and bigger in an unbounded way. We want to be able to keep all the variables bounded, meaning limited to a certain dynamic range, right? Okay, so so that's called BIBO, bounded input, bounded output stability, right? So how do you know if a system is bounded? There's a few different ways. So one way to do it is, so the problem with this is keep in mind that usually this is governed by, these systems are typically governed by frequencies, right? So you'll have a frequency response. I'm sure you guys talked about this in circuits, right? Where you have like, you'll have a circuit and you're giving it a sinusoidal input and you're looking at the gain. So you'll have a different gain and the gain will be a function of the frequency, right? Right? And also you'll get a different phase, right? Now in an LTI, a linear, linear time invariant, LTI, linear time invariant. In an LTI system, when you give it an input, a sinusoidal input, the output will be the same frequency. It'll be just a different magnitude, you'll have a different gain and a different phase, right? Which is, so basically you're looking at sinusoidal inputs. The problem is that, here's the issue. Some frequencies might be fine. You give it one frequency and it's behaving normally. Then you give it another frequency and then it blows up. It becomes unbounded. So how do you deal with that? Like how do you know which frequencies could potentially cause catastrophic, kind of amplification, right? How do you know? Well, you use trial and error. Well, no. What you do is you do an impulse response. So it turns out that there's this thing called an impulse, which is where you give it an input of 1 for an infinitely small amount of time. That's called an impulse. And that includes all frequencies. Like if you do the Fourier transform of that, it has all frequencies in it. The same thing happens if you give it a step. So if you go from 0 to 1 and just keep it at 1, a square wave, right? Square waves also have an infinite number of frequencies components. So you can either give, if you give an LTI, a impulse or a step, you're exposing it to an infinite range of frequencies, right? And so if any of those frequencies cause it to go unbounded, then the system will be unbounded. So the step response is not the step, but the impulse response is a common way to test for boundedness, okay? So that's one way to do it. There's another way though too. If you have the S-domain transfer function, remember I mentioned it's a ratio? So there's a denominator, right? So if you have a denominator with variables, in this case s, then there's a chance that the denominator can be 0, right? You could divide by 0, right? So the values of s that make the denominator 0 are called poles, right? Okay, so, and actually transfer functions always have poles. The problem is not having poles. The problem is that the s variable is a complex variable. And if all the poles, if all the values of s that cause the denominator in the transfer function to be 0, if they're all in the left-hand side of the plot, where the horizontal axis is the real and the vertical is the imaginary, right? If they're all in the left-hand side, the system is stable, right? What does that mean? Well, it basically means the complex part doesn't mean anything. Complex part you just kind of ignore. If the real part of the poles are negative, right, then the system is stable. Okay? So that's another option, right? The third is, so the first is finding the impulse response mathematically, right? The second is finding the poles. That's also mathematical. Another way is more of an empirical approach, where you can take the system and you can simulate it in MATLAB with a step or an impulse response or some kind of software tool. So this is an empirical way to do it, right? You just test it, basically. Yes?
This is a bit of a backtrack. Can you give the definition for what a plant is again?
Oh yes, plant is the thing that you're controlling. Right, so in this case, the plant is the toaster, right? It's the thing that, well, actually, that's probably a bad example. Because there's a controller that controls the behavior of the toaster, right? In which case the toaster is the plant, right? Even though the controller is probably part of the toaster, right?
Yeah, so you have like the controller, and then you have whatever in-device controller is like acting on and maybe taking care of something.
Exactly, yeah. Yeah, so it's like, you know, like it's like a still, like if you have a distillery, it's like the still where you're opening and closing valves in the plant to, you know, to distill something. Or like I said, in a car, if the, you know, you could think of like the steering wheel as the plant and you're trying to control, or the car is, you're trying to keep the car centered, you know. But yeah, you're right. It is kind of, usually the controller is part of the device that's being, usually it's, you know, that's why, I don't know if you noticed, but I had, that's why I say it's an embedded system. So the controller is usually embedded with the plant, but the plant is the physical sort of system that you're controlling. Does that make sense? Okay, so, right. Okay, so this is kind of esoteric, but bear with me here. Right, so I mentioned the impulse response, right? So what does that mean? It means that we're going to take the impulse and we're going to marry it to the plant, and then we're going to run it. Or actually, not run it, but define it as a combined system, right? Impulse, plant together, and then you can check for poles, for instance, right? Makes sense, right? The problem is that, remember, a transfer function is S-domain ratio times S-domain ratio. So what is the S-domain ratio of an impulse? I mean, what is it? Like, it's, because impulse is like, it's this weird thing where, you know, you essentially give it a 1 at time 0, and it's 0 everywhere else, right? Well, it turns out that the impulse, believe it or not, is literally just a constant 1 in the S-domain. Right? So if you just have 1 in the S-domain, it's the impulse, which means that you can find the impulse response by multiplying a transfer function by 1. Right? Now, what about the step response, though? What if I want to put a step in? Like a 0 and then it becomes 1. What is the S-domain description of a step? Well, it turns out it's 1 over S. Right? But no one uses the step function because the impulse is just as good for testing stability, and it's much simpler. You don't have to worry about 1 over S. It's just 1, right? Okay. So, right. So this is pretty cool. So let's say you have a transfer function like the one here, okay? I just made this up. No, actually I didn't make it up. It was from the earlier slide where I showed how to convert from time domain to Laplace. But anyway, this is a transfer function. How would I generate the impulse response in the time domain? How do you do that? Now you might say, well, wait a minute, you don't need to do that. You just look at the denominator, you can find the poles. Yeah, I know, right. But what if I actually want to draw it? What if I want to draw I want to see what exactly happens when I hit this guy with an impulse? How does that work? Well, it turns out you can do that sometimes. So basically, the idea is hold on a second, these are out of order. Oh, right, actually, wait, before I get to that, sorry. The first thing I did here is I want to figure out what the poles actually are. So you start out here and you want to find out which values of S are going to make the denominator 0. So in order to do that, I just multiplied the numerator denominator by S, right, which put the denominator into a polynomial that I could factor, right? And so then I factored this guy, and this is basically, turns out, I just use algebra. and I've got s over s plus 3 times s minus 2, right? Now, once you have it in this form, it's very easy to figure out what values of s will make the denominator 0. You just find the roots here, right? So obviously, if s is negative 3 or s is positive 2, you'll have a divide by 0. So those are going to be your poles. Make sense? Now you might say, I thought you said those were complex numbers. I thought s was complex. It is. There just happens to be, in this case, the imaginary part just happens to be 0, right? So all I get is the real part. Now, is this a bounded or unbounded function? Well, it turns out it's unbounded because one of the real parts is positive, right? Or 0. S minus 2, right? If s is 2, right, I'm going to make that denominator 0, and that's going to be my pole, right? So it's unbounded. So you can, yeah, so there's the poles there. Okay, so now I know it's unbounded, but so if I hit this guy with an impulse, it should blow up, right? But how do I know that for sure? How do I show that? How do I do that? Okay, so this part is kind of neat. So now we have to do an inverse Laplace transform because we got to get this back into the time domain. But we don't want to put it back in the time domain with the integrals and derivatives. We want to put it in the time domain that it'll literally render the actual impulse response. You guys with me? Or the step response. But if I do the step response, I have to multiply this by 1 over s first. Impulse response, I don't have to do that. If I just take the raw transfer function, I'll get the impulse response if I can do the inverse Laplace transform. So how do you do that? Well, it's really tricky. So the way that it's done, believe it or not, this sounds crazy. At least to me, it sounded crazy. But people use just a table to do inverse Laplace. They literally look it up on a table, right? So one of the ways to do it on a table is if you have 1 over s minus a, the inverse Laplace transform of this is exponential a times t, right? So we go from s domain here to time domain here, right? We go from right to left on this table, right? However, the problem is that in order to do that, you have to have the s domain in exactly this form. It has to be 1 over s minus a, meaning that this is disqualified, right? I can't directly convert, I can't directly do the inverse Laplace transform from this form because it doesn't match 1 over s minus a. It's more complex than that, right? So how do you figure that out? Okay, so there is a way to do it. Okay, so you have to use some trickery here. So I can say, if I take this, I want to represent it as a over s plus 3 plus b over s minus 2. That way I've got these two components that match the inverse Laplace transform rules, right? The problem is that I don't know what a and b are. And to add even more problems here, a and b are unknowns, means I have two unknowns, but I only have one equation. So you can't solve for two unknowns with one equation. That's impossible. That's an underdetermined system, right? It's impossible. Well, that's what I used to think, but it turns out it is possible. You can do it. Okay, the way you do it is you basically take those two guys and recombine them, right? So now, again, this a over s plus 3 plus b over s minus 2, that's like a hypothesis, right? I want to get it into that form. So I will take, I'll find the common multiple, which is a times s minus 2 plus b plus s plus 3, right? And the denominator is now the product of those two terms, right? Makes sense? Right? So basically I cross multiplied there. Okay, but then I still have this issue because I need a and b. There's two equations, two variables with one equation. So this guy, I can get rid of the two common denominators on both sides. So that's s equals a times s minus 2 plus b times s plus 3. And then check this out. Let's say s happens to be 2. If s happens to be 2, s minus 2 will be 0, and it eliminates a from the equation. And now I have one equation with one unknown, right? If I just assume that s is 2, what if s is 2? Then that whole a term goes away, right? Then I can solve for b. And then likewise, if I set s to -3, s plus -3 is 0, that basically eliminates the b term, so then I can solve for a. So I can solve for a and b. I solve for two unknowns with one equation. That's amazing. It doesn't always work, though. It only works if those roots are unique, right? But that's pretty cool, right? I solved an underdetermined system, right? So then I get this. This is a and b. A is 3/5 and b is 2/5, right? Then I can do the inverse Laplace transform of this, although it's done in two parts. And these become my, what they're called eigenfunctions, right? So you can basically use the table. So if I take this, which is what I just solved for, and I do the inverse Laplace transform, I get, and this is from table lookup. I have no idea how this really works. But if you do the Laplace table, you get 0.6 e times 3 to the power of -3t, and 0.4 times e to the -2t. Then all you have to do at this point is just plot that with respect to t. Now you might say, wait, whoa, what happened to the input? Where's the input? Well, the input is baked into this because the step response is baked into the transfer function, right? So if you plot this, you actually get, obviously it's unbounded because of this term, 0.4, this is 0.4 times e raised to the 2t power. So obviously, that's going to blow up as you increase t. But so that means it's unbounded. But even what's cooler about it is the fact that you actually get the real step response. That's literally what would happen if you hit that transfer function with a step response. So you're not just learning that it's unbounded. You're learning what it actually will look like. Like at what point will this knuckle, tells you where the knuckle of the curve is over here, where it starts to, where you get unity gain, where the slope becomes 1 and it shoots up the space, right? So you get a unity gain point here. But anyway, that's how you can do a inverse Laplace transform. I'm out of time.